OK, so let's solve this. So first, let's draw a picture. So here's our Earth. And we have some car that's rolling on the Earth. And the car is going to be accelerating. So in order to accelerate, we know that the car must exert a force on the Earth such that the Earth exerts a force back on the car. This is just like the locomotives question in the previous module. So the force of the car on the Earth is equal and opposite to the force of the Earth on the car. And so this leads us back to impulse. So we know that the force of the Earth on the car times the change in time is going to equal the change in momentum of the car. But we know that the force of the Earth on the car and the force of the car on the Earth are equal and opposite. So we know that the force of the car on the Earth, which is going to act for exactly the same amount of time, is going to give us the change in momentum of the Earth. And so the change in momentum of the car and the Earth is exactly the same, because these two forces have the same magnitude. So these two things are equal. And so that's going to give our correct answer as number 2. Now, clearly, there's one thing that we can say here. We know that the change in momentum of the Earth and the car is the same. But of course, we don't see the Earth swinging away backwards at high speed. Again, this is for the same reason that you don't see the Earth accelerating up at you when you fall towards it, because we know that the mass of the car times the velocity of the car that it finally attains is going to equal the mass of the Earth times the velocity of the Earth that it attains in this procedure. And so clearly, the velocity of the Earth is going to be equal to the velocity of the car times the ratio mass of the car over mass of the Earth. And so since this ratio is a really, really, really small number, we can say that the velocity of the Earth is a really, really small number. And so we don't see the Earth whizzing away backwards as the car goes forwards.